While the panelists are taking their place at the podium, I'll start the introduction. Now, I'm Nick Arndt. I'll be moderating this debate. This debate, whose title is given there, Impact was not the main cause of mass extinctions. Now, the first of the EGU great debates in the Geosciences was held in 2003, I think it was, on a very similar subject. Again, the subject was, what was the cause of the mass extinctions that punctuate the evolution of life on Earth? And was this mainly due to impact of a meteorite or meteorites, or some other cause, volcanic extinctions, volcanic eruptions? This will be also the theme of today's debate, for which the motion is, as I said, impact was not the main cause of mass extinctions. We're having this as a semi-formal debate, in that there are two teams, each charged with defending the motion or arguing against the motion. So those arguing for the motion, which means they think that impacts were not the main cause, we have, and let me check this, we have Blair Shaner from Princeton University, and Evelyn Kutatscher from Naturmuseum Südtirol, from Austria, an Austrian participant. Italian, so, okay. Sorry, Südtirol. That's why, now I understand why the telephone had an Italian number. I thought, sorry for that mistake. But the other speaker is indeed Austrian. He's Christian Köbeln from Vienna. He's the director of the Natural History Museum. And he is arguing against the motion, which he'll be defending, remarkably enough, impacts. And then the last speaker is Paul Wignall, who got the medal this morning and gave an excellent talk in which he seemed to be arguing for a volcanic connection. But today he's going to take the opposite side. He's going to be arguing that impacts were the main main cause of mass extinctions. Now, this is a debate. But the way it's going to happen is that each speaker will have 7 minutes. So we'll start off with Blair, who will give the first talk, 7 minutes, and then Christian will follow for the other. Paul, okay, Paul's going to start. Okay. Well, I thought we had this all sorted out. Anyway, we'll huh? Okay, so Paul is then going to speak against the motion, and then Evelyn, and then Christian. We do it that way. I've stressed that this is a pedagogical, a rhetorical exercise. The speakers will not be giving their heartfelt, firm convictions about what they think is the correct interpretation. They'll be given license to defend their side of the debate. And I stress this because we want to clearly distinguish between the two different sides. So what's going to happen? We were to have another speaker, Paul Rene from Berkeley, and he couldn't make it. And he sent a message last week, which is too bad, but we still have 4 excellent panelists, and we can do it that way. We're going to have these 4 presentations. Then I'll probably ask 1 or 2 penetrating questions to see if there are any weak points in the argument of one team or another. We'll give the panelists a chance for a rebuttal, and then we'll open the floor. You can ask questions for a while, and then finally we'll finish up with round-up statements by each of the panelists. Oh yeah, and one other thing we do in these debates, we start by asking you, the audience, for an informal vote to see which side of the motion you favor. We'll do this now, and we'll do this at the end of the debate to see if the power of the oratory, the lucidity of the arguments presented by the panelist will assuade your opinion. So let's have a quick vote. Now, who is for the motion, which means you do not think that impacts with main cause, you mean that something else was the main cause. Show of hands if you're for the motion. Okay. And those who are against the motion, who think that impacts are the main cause of mass extinctions. Well, what do you think? It looks to me pretty, the two groups are pretty equally pretty equal, yeah? Yeah? We'll see, but now we'll have the debates and we'll see what happens for the final vote after the presentations and the discussion. So without further ado, I'll ask Blair, you're going to start off.
I guess so.
Arguing for the motion that impact was not the main cause of mass extinctions.
Okay, thank you for the opportunity to be here and have this debate. Okay, so in my 7 minutes, I want to make 2 main points, and one is to start with this diagram here that you've all probably seen before. I guess 10 years ago when this debate first started about the similar topic was about when this diagram was made. Similar diagrams have been made in the past, and admittedly, it's a diagram where if you plot it as such, everything will fall on a one-to-one line. But what it has put forth is the opportunity to target and study some of these extinction events in more detail. And so, in particular, the big ones, such as the end Permian, the end Triassic, and the end Cretaceous have received a lot of study since that time. And one of the things that has been very important is establishing a better chronology for the correlation between these events. And so I'll just highlight a couple of those efforts. This comes from a paper by Burgess and Bowring recently, establishing a tighter correlation between the end Permian mass extinction and the Siberian traps. And what they show is that the onset of volcanism at about 252.25 or something like that starts about 200,000 years before the main pulse of extinctions at about 251.9. So volcanism actually started several 100,000 years before the main extinction event. And if you were at the extinction session this morning, we saw evidence from Josh Davies that there has now been discovered older camp magmatism that began about 200,000 years before the end Triassic mass extinction as well. So a very similar timeline. And in both those cases, magmatism carries on for several 100,000 years after the extinction event. Now, this holds up for the end Cretaceous mass extinction as well. Recent geochronology has placed a much tighter timeline on this sequence of events. In particular, the onset of the main phase of the Deccan Traps volcanic event has been shown to start about 250,000 years before the main pulse of extinctions at about 66.04. The diagram on the left simply shows the osmium seawater isotope curve, which sees osmium isotope values plummet in seawater starting about the same time at the C30N to C29R magnetic reversal, which is interpreted to reflect the onset of the Deccan Traps volcanism. Similarly, recent efforts from argon dating from the group at Berkeley, from Paul Rennie, since he couldn't be here, I put his diagram up here, agrees very well with the uranium-lead data that shows that the volcanism starts about 250,000 years before the extinction event and carries on for about 400,000 years afterwards. So there's a stark similarity between these three of the largest mass extinction events in the last 500 million years in terms of the sequence of magmatism and extinction. Now, because the Chicxulub impact occurred at the Cretaceous-Paleogene boundary as well, you might ask the question of how do you actually distinguish the effect of the Deccan Traps in this event. And so one way to do that is to establish that, in fact, environmental deterioration and extinction started before, in fact, the impact. And so I'll highlight a few examples of making that case. So here's a diagram on the left establishing paleotemperature records from fossil leaves from Wilf et al. 2003. And what you see here is time, basically stratigraphic height, in which they show there's a dramatic increase in temperature a few 100,000 years before the main pulse of extinction event, and then a dramatic cooling leading up to the extinction. Similarly, oxygen isotope values from forams from Lee and Keller, 1998, and other examples of foram records as well, show that there was a similarly parallel increase in temperature beginning somewhere around the C30N, C29R magnetic reversal, and then a subsequent decrease in temperature leading up to the boundary. Okay, since everyone is a big fan of mercury these days, I thought I'd show some recent mercury records from the late Cretaceous. Mercury is thought to be derived from volcanic events and carried globally and deposited in sedimentary records. And what you can see is that mercury anomalies, this is from a section in France, you see an increase in mercury beginning about the same time as the Deccan traps, about 250,000 years before the boundary. Importantly, this is just a record of volcanism, but also mercury, along with other heavy metals, can also lead to poisoning in the environment and may be a contributor to the extinction event itself. And other records, here's some paleotemperature records from Delta 18 records from mollusks, where, again, an increase in temperature and then sudden decrease right before the boundary was observed. And in the same study, they looked at extinction rates across that interval and made the case that there was in fact two pulses of extinction, one that began long before the Chicxulub impact event in the middle of C29R. So evidence that the extinction event actually began before the impact. And finally, another record from clumped isotope paleothermometry of fossil carbonates. These are from Montana. Again, show a dramatic increase in temperature beginning about at the C29R magnetic reversal, and then a decrease in temperature. This gray curve is the one I showed you before from the fossil leaves from Wilf et al. 2003. And plotted on the right are estimates of mammal evenness. This is basically a proxy of biodiversity in mammals, again from Montana, showing a decrease in biodiversity leading up to the boundary, again arguing that there was significant environmental perturbation and onset of extinction in mammals in Montana before the Chicxulub impact. And so the conclusion here is that the Deccan traps, in fact, played a very major role in the extinction, if not the only role. And you must then ask the question, was the Chicxulub impact actually necessary for the extinction event?
Well, excellent timing, very powerful arguments, I thought. But now we have Paul Wignall, who's going to make the first speaker who will make the case for impacts, having a major impact on the extinctions.
Okay, thank you, Nick. So those of you there this morning when I was talking about large igneous provinces and mass extinctions might find it strange that I'm now defending impacts, but one of the sort of take-home messages from my talk this morning was that large igneous provinces, in fact, don't correlate with all that many mass extinctions at all. So you can see this plot here, the hit-miss ratio is 6 out of 15, which is not that good. And if you take out the Deccan traps from that correlation, then you're down to 5 out of 15. Now this plot, as you can see here, from work that Dave Bond and I did a few years ago, if you'd extended it back to the Cambrian, you'd see more extinctions there, of which none of them correspond to large igneous province eruptions either. And so in the absence of an obvious volcanic cause, then maybe we should be looking at other causes, such as bolide impact for a lot of these. And even for things like the end Permian, there is evidence out there in forms of shocked quartz and so on for impact at the PT boundary as well. So, although volcanism is obviously a lot of people's favourite extinction mechanism, it doesn't always fit. So this is Blair's work again, who's just showing this, and obviously the debate, a lot of the debate about this is whether the Chicxulub impact, which is our sort of our type example of a bolide-generated mass extinction, is it wholly or partly responsible for the end Cretaceous mass extinction? To which I will argue that it's entirely responsible for the end Cretaceous mass extinction. So these are the dates that we have, some of the best dates we now have for the onset of Deccan eruptions, which you can see here is around the base of C29R magnetochrome, and then the mass extinction itself happens up there towards the end of that chrome. So the question is then, this is at least useful, at least these two events are separated in time. So what happens in the intervening 250,000 years? So the best way to look is look at the fossil record. So there's been obviously plenty of work done on this. This is one of the more up-to-date studies. Dinosaurs are the famous victims of this extinction, and this is a work done by a series of dinosaur experts led by Steve Bussati in 2015. Looked at the range, they had a whole series of data sets. This is the data from North Dakota, as you can see. And their conclusion was, as you can see there, that all the dinosaurs died at the end of the Cretaceous, coincident with the mass extinction, with the bolide impact. If you put on the onset of the Deccan eruptions, which you see here, somewhere down near the base, then nothing disappears at this point. So certainly the start of the Deccan eruptions causes nothing, basically, in terms of losses. You can see, obviously, the dinosaurs start dropping out a little bit earlier before then, and that's almost inevitable. Dinosaurs are not common fossils. The chances of finding every last individual of a dinosaur species at the very end is going to be pretty slim, and so the concept of backsmearing, which has been around for a good sort of 30-odd years, whereby certainly some of the rarer fossils disappear slightly before that. To avoid that problem of the quality of the fossil record, you can have a look at other fossil groups. So this is a study done by one of my students, James Witts, and colleagues, and this is looking at the ranges of marine invertebrates from one of the most expanded marine sections available, which is in Antarctica. And so the beauty of this section is it's about as good a sort of fossil record as we can get for the marine invertebrates. And as you can see, as I marked on there, the main extinction and nearly the entire extinction is right at the KPG boundary at the time at which the bolide hit, with 24 out of 34 species disappearing at that point in time. So if we look where the marked on, to the base of 29R is just down there. If you draw it on precisely, then nothing disappears at that point, and not much in between either. If you actually extend, if you say, well, maybe the boundary, there's a little bit of error in the dating, you could say that maybe 4 species disappear on or around the onset of Deccan eruptions, and, well, that's not particularly significant, and in fact you could choose any random line through this chart and you'll find 4 or 5 species disappearing at any point. So for this community living in the Antarctic, then everything was fine until the very end of the Cretaceous, and then they all died probably overnight as a bolide hit the planet. So I'd argue that certainly for the Deccan traps, their role in any sort of extinction is extremely limited. I'm not denying that there was interesting environmental effects with sort of warming onset and so on, but we're talking about extinction here and whether bolides cause extinction, and I think, yeah, the Deccan traps can't be implicated in that at all. One of the things about Deccan eruptions is if you want not the bolide to do it, but if you want the large igneous province to do it, then you can model the effects of that, and particularly look at the sulfur dioxide and aerosols effects. And this is the work of colleagues at Leeds. Anja Schmidt led this study based on adapting a model which is used for the modelling of modern-day aerosol concentrations in the atmosphere, and basically looked at the effects, as you can see, there's a few scenarios here. There's 2 closely spaced eruptions here. This is looking at the cooling effect of sulfur dioxide. So there's 2 closely spaced eruptions in blue, and then there's if there's a more prolonged large eruption in orange. The problem with SO2 and the problem of these effects of these eruptions is they are interesting, quite large, but they're not that effective, if you see what I mean. So there's in total cooling events of 6K based on that, and then we can look at there's been the incredibly explosive eruption of Toba 74,000 years ago, and using the same models, they about 10K of temperature drop for that particular event, and the Toba eruptions cause no extinctions, and there's no reason to think that the Deccan eruptions will cause any extinctions by this mechanism either. The other possibility that's been mooted for volcanic eruptions is, for Deccan traps, is looking at acidification effects, and again, Part of the problem is that it just doesn't stay in the atmosphere for very long. So this is modelling a Deccan scale eruption, which erupted in the southern hemisphere, and this compare it with a Rosa scale eruption level there, and looking at in effect the the intensity of volcanic acids or acidic smog in the ground level in these regions, and how far away you can get it to have an impact as well. And basically, you can't get it very far beyond that sort of equatorial latitude before it all gets rained out and it's all removed out of the atmosphere. The Rosa eruptions of the Columbia River, again further north, but less intense because it's less large eruptions as well. So none of these things seem particularly world-ending, catastrophic scenario for extinctions. So LIPs, they struggle to do anything devastating, is my argument. So therefore, we need something bigger, like a bolide impact. So just to finish with a terrifying picture of something large, and bearing in mind the roles of acidification, one of the things, particularly at the end of the Cretaceous, is that the amphibians, of which here are some Cretaceous amphibians, a very, very large toad, do fine at this boundary. This is a group that should be extremely susceptible to acid rain and acidification of freshwater ecosystems, but they're not. They survive, they hop across the boundary, and do perfectly well. So it's in terms of the Deccan eruptions, it's hard to see how they're causing any effect whatsoever on the biota. Okay.
So thank you, Paul. Yeah, also some very convincing arguments that I'm not quite sure how the 4 team will be able to counter them, but Evelyn will have a try.
Yeah, thank you very much. Since Paul sort of finished his talk with the name biota, I will go on with that one, more or less. Here you have just the modeling with the extinction rate and the diversity increase through time, and you see several peaks in this curve which sort of indicate the mass extinctions. So if you think about the mass extinction at the PG boundary, so at the end of the Cretaceous, what always comes up if they do debates if it was more of an impact or if it was more the information of the volcanism. But let's have a look at the real data on the biota itself. So if you look into the marine invertebrates at the PG boundary, what you can see is that you have a nice extinction rate over here, and some survivors and high stress tolerant plants. And of course, everybody else collaborates as well, or almost it seems like that. The dinosaurs also appear to be extinct completely at the Cretaceous tertiary boundary, and only few recent groups survive. But let's have a look also on some minority groups. What happens with plants, for example? If you have an impact, or if you have whatever is happening on the continental side, you would have expect to see quite an influence also if you look into the, let's say, continental sphere, especially the plants which are the first one to interact with atmosphere. And if you look here at the KT boundary, what happens is almost nothing. Actually, apparently, are completely not affected at all by this event. Something similar is if you look into insects. Also here, if you look at the Cretaceous tertiary boundary over here, okay, they are only considered the pollinators in this case, but still you can see that there is a nice decrease in diversity when nothing happens at the boundary itself. So that's for the big impact from the Cretaceous. Now let's go into the second case, which is the Permian mass extinction. In this case, what you have is mostly ellipse, so mostly volcanic activity in here. Also here you can see a wonderful extinction event up to the boundary, mostly for invertebrates, for marine invertebrates, which is mostly talked about normally if you think about mass extinctions. And again, let's have a look at the continental side of the whole thing. And if you look again here into plants, then you can see they have a nice increase into the Permian, and then at the end of the Permian there's a decrease here, but well, it is some decrease, there's more decrease at least during the Cretaceous, but even there you can see that something happens before or even afterwards. Something else, the colleagues of mine from the University of Zurich in the last years have been putting together a lot of data from palynology. So here again, you have the Permian-Triassic boundary, and what you can see that even before the transition, you have a first ecological crisis, but you have several crises even afterwards, and you have going forth and back, so you have a very instable environment. That's not something that happens if you have one impact system. So if you expect to have an impact, or in any case a one event system that creates the mass extinction, that is not the result. That's not the result you were looking for it. So if you use the color overview from 2009, you can see here all the mass extinction intensity, here the PT boundary, here the KT boundary, and you have here all the impacts or known impacts and the datings for that, during that time, the datings of the volcanic event. And what you can see is that some of them here are correlating quite nicely with mass extinction, but a lot of them also correlate with LIPS, so with these large igneous provinces, with volcanism. There are even some mass extinction events like here at the end of the division. We don't agree with anything like that. And my consideration about that is that especially something like one event system like a meteorite, but also perhaps some LIPS are only too simple as a result in order to really explain what's happening with biota. Thank you.
So thank you, Evelyn, and we'll pass straight on to Christian, who will be the last speaker for the second team, who will argue in favor of impacts.
Yeah, thank you. I'm not a paleontologist, so I can't show you wiggly lines because it seems to be possible that you find wiggly lines in favor and in opposite favor, no matter what you want to propose. I want to introduce impact first as a planetary process and then show you what kind of influence it might have on the Earth. So if we want to look around in the solar system, our cosmic neighborhood, how does impact fare? Now, impact is currently the most dominating and the most important surface forming and surface modifying geological process that exists. If we look at our moon, it records impact events over the last several billions of years. If you look at other planets and satellites with solid surfaces in our solar system, they are covered with impact structures. Mercury, the innermost planet, looks like the moon. It has impact craters covering the whole surface. Venus, despite having a very dense atmosphere, which prevents some of the smaller asteroids from crashing on the surface, is covered with impact craters. It was resurfaced probably about 700 million years ago, and nevertheless, hundreds of large impact craters have been found on the surface of Venus. Mars, our next cosmic neighbor out there, is covered by impact structures. There are large volcanoes, no doubt, but the main surface dominating geological process is impact. The same is true if you go in the outer solar system and look at bodies that have solid surfaces. They're all covered with impact structures. Even the asteroids, of course, the main culprits that we think are the causes of all these impact events, show the results of collisions among each other. And so when we go and look at asteroids, we have currently a database with approximately 700,000 or 800,000 asteroids between Mars and Jupiter that have known orbits. Of those, about 20,000 or so are in possibly Earth-crossing or Earth-approaching orbits. And I show you here a subset of these asteroids, only those that are larger than approximately a kilometer in diameter. We're truly sitting in the middle of a cosmic shooting gallery. Now, why do we want to study impact craters in the first place, and what is their geological importance? Now, they are unique geological features on the Earth. On the moon, they're easy to recognize. They dominate the surface. There are no geological processes on the moon that obliterate impact structures rapidly like they do on the Earth. So on the Earth, it's actually not quite so easy to find impact structures because we have an active hydrosphere, an active atmosphere, we have active geological processes, subduction, volcanism, etc. going on that with time obliterate impact structures. So we do need some good evidence to identify them as opposed to the more obvious impact structures on atmosphere-less or atmosphere or low atmosphere bodies. We need very clear mineralogical, petrographical, and geochemical characteristics to help us identify impact structures because they might be eroded, they might be covered by younger sediments, and so on, and therefore you need criteria to identify them. And this is what has been done over the last about 30 years to identify a set of these criteria. But the most important part is impact is a short-term, extremely high energy, violent geological process. And this is something important we're going to come back to at the end here. Now, of course, the subject of the debate is mass extinctions, and we all know that one of the main reasons why we actually have this debate was that around 1980 there was a publication that showed evidence for an extraterrestrial event, an impact event, coinciding with the already well-known Cretaceous Tertiary or Cretaceous Paleogene mass extinction. Now, I'm showing you here a picture of a particularly well-labeled boundary, which is in Italy, not far from the location where the first discovery was made. And I want to make that point again. People were not looking for the cause of the mass extinction at that point. They were looking for something totally different. It was a chance discovery. They analyzed, there was, of course, Alvarez and colleagues, they analyzed the chemical composition of this layer as they analyzed the chemical composition of the rocks up and down. And by chance, they found evidence for impact in between. And by chance, this coincided with the main extinction event. Now, time, of course, told us what else there is. We have interelement ratios of platinum group elements. We have chromium, osmium, tungsten isotopic compositions of this particular thin layer that indicates very clearly that a large asteroid of carbonaceous chondritic composition hit the Earth. We have a soot layer. We have many other lines of evidence there. And most importantly, we have a lot of shocked minerals that are found exclusively in this layer and not anywhere else except, of course, for bioturbation. Shocked quartz, shocked feldspar, shocked zircon, you name it. There's all these shocked minerals that are found in there. They're found worldwide. There's locations all around the world where you find these shocked minerals and the geochemical anomalies that point towards impact. It took over 10 years of intense search because on Earth, as I said, impact structures are covered up to find where the KT boundary impact structure was located. Chicxulub, we all know about it. There was a recent IODP, ICDP drilling program there. You can hear more about that tonight, even in the ICDP, IODP town hall, and I don't need to talk too much about this. We now know for sure that Chicxulub is an impact crater. It is the same age as the KT boundary, and you find ejecta of the Chicxulub impact directly within the KPG or KT boundary layer worldwide. There are effects of this very short time high energy event that range from minutes to millennia, even to hundreds of millennia. Greenhouse effects, fireball, dust, acid rain, you name it, it's all there. How often do such things occur? We know that because we've dated impact structures on the Earth and elsewhere. And we know that small impacts are fairly common, but a large one, about the Chicxulub size, maybe every 50, 100 million years in Earth history, documented by past impacts. Now I want to kind of end on a brief note here, reminding you that these things happen all the time. Just a few years ago, there was a large explosion of an asteroid that didn't even make it to the ground, that exploded in 25 kilometers altitude over Chelyabinsk. It broke windows, it flattened walls, 1,500 people were sent to hospitals. That was 65 kilometers as the crow flies almost done. And this was only one of many, many such small airbursts that happened over a period. Here you have a 20-year period. So these things happen all the time, and I'll skip over this. We can talk about that later. And I'm just contending that there is nothing like finding the smoking gun, and I think we found it.
So excellent. No, we had 4 good talks, and I've tried to make now I have to ask some questions. And what I got out of this, there seemed to me 2 main type of arguments. One argument concerns the coincidence or not between extinctions on one hand and either impacts, or we really just mainly talked about LIPS, large igneous provinces. And Paul, you gave a score. The score for LIPS was only 5 out of 15, which is not very good. But what's the score for impacts? You know, there are extinctions throughout the history of life. And what's the score for the impacts? How many impacts do we know that coincide with any of the extinctions other than the KPG?
There's a good one. And there's, my point is that in the absence of a kill mechanism, then you need to start looking for evidence which is hard to find. And so for extinction events like the end Ordovician, late Devonian, end Devonian, we still need a driver for those. And so there is tentative evidence, particularly in the Devonian, for impacts at the time of some of the minor extinction events there as well. So yes, a large igneous province is easy to spot, so therefore, not surprisingly, we've managed to find the links between them, but the evidence from impact is little tiny bits, little grains and things like that, so you're looking for harder evidence.
Okay. So then I'm going to ask Blair the complementary question. There are a lot of LIPS, the young ones. Why did the young LIPS don't seem not to be associated with extinctions?
Hello. Sorry. Well, the answer to that is pretty simple, and it's that the young LIPS are much smaller than the ones that actually resulted in mass extinctions. For example, the Ethiopian eruptions and the Columbia River basalt were much smaller in magnitude. Columbia River basalt on the order of a couple 100,000 cubic kilometers compared to those that resulted in mass extinctions on the order of several million.
Yeah.
And the rates of eruptions, of course, are very important too. The North Atlantic igneous province, the geochronology is not very well established, but potentially took place over a much longer period of time than these that resulted in mass extinctions. So establishing the rate of both eruptions and then the flux of volatiles that may have been the killing agent can't really be established for those.
Okay. So you're allowed to come back, Paul, Christian? Is that acceptable argument?
I don't think there's any link between volume and extinctions. The Emishan and Middle Permian extinction is a very small province, so it's the same size as the Columbia River virtually. So.
Okay. So Evelyn, Paul mentioned this intriguing gap of 250,000 years between the onset of Deccan volcanism and a period when he said nothing much seemed to happen. Is that right? Is that the way you would interpret it? 250 million years since the onset of Deccan volcanism and, in fact, the Chicxulub impact.
Well, if you look into invertebrates, of course, then you have a continuity to the whole thing. If you would look into the dinosaurs, for example, then you have an extinction which is starting already before. So it's not that it's only, so the invertebrates more or less go up to the boundary. While if you look into the tetrapods, for example, then you actually have some start of extinctions beforehand.
Mm-hmm. Okay. And the other sort of argument that I saw was some attempt to estimate the damage created to the environment, the impact of impacts on one hand and volcanic eruptions on the other. And I think, Christian, you argued that impacts were unique, catastrophic, and so on, and would have had a much greater impact. On the other hand, is it correct that aren't there other impacts, craters that we know through Earth history, which seem to have had relatively little effect on the global environment?
I think, yes, there have been larger events, but they were all in the Archean as far as we know. And we have not an easy way to establish what the effect on blue algae and so on was at the time. There might have been extinctions of blue algae, but the record is rather fickle at this time. What I think is important is that when we look at impact, the energy that is released within a very short period of time, within a very, very short period of time, and we're talking basically about seconds here, is so far in excess of anything that any terrestrial events can release within that period of time, that the energy density that you introduce into the environment is very, very severe indeed. And even that small explosion that I showed towards the end had 30 times the amount of the Hiroshima atomic bomb. And if you look at a KT event, then you have like, I don't know, millions of times or hundreds of millions of times of the largest atomic bombs that we have on Earth. And so it's the energy density that counts that you introduce within a short amount of time.
Blair, do you have a comment on that? Have you thought about how much? Well, this is the direct comparison. How devastating for the environment is a large eruption of a large flow if we also add thermogenic gas release and so on? How do you compare the two?
Well, I'd say the actual energy being released is not necessarily the important factor, but the effects of what is being released. And in the case of large igneous provinces, we have many things that are released, be it carbon dioxide, sulfur dioxide, halogens, poisonous metals that are expected to result in deleterious effects in the environment.
Okay.
As a short comeback, the amount of energy released, I agree, if you can accumulate things over some time, but you do see the effect of the extinction at the KT boundary, for example, precisely at the time coinciding with the impact event. You don't see all these large effects happening hundreds of thousands of years before or after while the eruption still went on. And we do release, especially in the case of Chicxulub, also a large amount of sulfur dioxide in the atmosphere, sulfur trioxide, and there are poisonous metals and so on. And we have 30,000 cubic kilometers of dust that were blown in the atmosphere. And let's not forget, with such large-scale events, we blow off a major part of the atmosphere, and we introduce catastrophic fire rain that set things on fire on a very short period of time as well. So there is a very important effect, and the problem is that the geological record is not very good at preserving short-time events because of things like bioturbation, things that happen with millions of years. It gets diluted and gets spread out a little bit, but it doesn't get obviously spread out enough that we have the effects over hundreds of thousands of years, which is what would be required if volcanism is the main cause.
Evelyn, you wanted to have
I was thinking about the effect of the catastrophism in the meteorite. That's one more event, which is very high energy, but that means that from a certain center out, it spreads over the world. Now, that means that it's not selective at all to species level, because whoever it gets, it kills, and whoever survives, that one survives. So even if only, let's be biblically, 2 individuals of one species survive, the species would persist. While you, on the other hand, to kill out entire bioplants or entire groups of organisms, what you need is to change the environmental conditions in such way that none of the individuals of that single species or family or whatever else can survive that, which is not something that can come over in one single event. It's not just a simple like an impact and energy.
Okay. Paul, do you want to? Go on.
Yes, I mean, in a sense, there is selectivity at which links in with bolide impact at the end of the Cretaceous. Anything that relies on photosynthesis at the base of the food chain was in trouble, which I think is why freshwater ecosystems do quite well, because they're based on organic detritus. The various things like tadpoles and frogs and things like that are grubbing around in the sediment at the bottom, so they're able to withstand days, probably months and a few years even, without any sort of food to eat, any plants to eat, because they're not eating plants. Whereas anything on land or the base of the food chain in the water column, they're the things that do really badly there. So if you want, bolides will black out. I think we didn't really talk about the actual way a bolide will kill things. It's just a blackout. I think it's several years of blackouts, and so you end up very cold, very little photosynthesis going on. So I think KT fits very nicely with that scenario.
Okay. So should we open ask for questions from the floor now? After you've heard some of the main arguments. And now if you'd like to ask a question of any of the panelists, the microphones are there. There's one midway. There are two of them in the central aisle. If you want to ask a question, go up to the microphone and try to ask a short... Yeah, there's somebody. Somebody's going to get up. Try to keep the questions short and simple. You can make commentaries if you like, but keep them short. Ask a question of one of the four panelists.
So, Christian, I've got a question for you. You're talking about evidence, shocked quartz, shocked zircon, geochemical anomalies on the KPG boundary. Do you see these anomalies on the other boundaries as well?
Very limited evidence for that at this point, but I think we're probably trying to compare apples and oranges in a way here, because the question is how well preserved are some of these boundaries. And let's not forget that people needed to search very long time and very detailed, even at the KT boundary. So I think there is evidence, as Paul already mentioned in the Devonian, there's some evidence in the Ordovician that there is impact evidence, but the correlation is very difficult to make. Where we have contradictory evidence, I would say, to be honest, is at the Perma-Triassic boundary. There has been evidence published, it is contradictory, so.
So we have three questions, one there, two, three.
At the beginning, we were put the question, who votes for the motion, who against it. I was missing a third alternative.
No.
And my question to the panelists is, do you think it's possible that we have mass extinctions which have volcanic origin, for example, but by coincidence were fortified by impact? That's what my belief is for the KT boundary.
Okay, so who would like to respond to that?
Well, I point you to a recent paper that was published by Mark Richards and colleagues, and Paul Rene, who was supposed to be here, whose opinion is that the Chicxulub impact triggered the main part of the Deccan eruption. So in a way you have a billiard ball effect.
Happy with that, Blair? Huh?
Well, in the spirit of debate, I would just answer no.
So, next question.
Yeah, about the extinction effect, you mentioned the high energy density for an impact, but you didn't talk about what is the post-impact winter, so like nuclear winter. So what is the effect actually on the overall global biota of the winter that follows an explosion?
I think that's the cause of the extinction. I mean, it's the global winter. Is that what you mean?
Yeah.
I mean, the immediate effect is on photosynthesis.
So then it's not so much directly linked with the energy density of what, it's more the amount of opacity that was created for a given time in the atmosphere.
Yeah. All right. This was the idea of one of the diagrams that I had, and I had to rush over it a little bit. We have short-term and long-term effects of the impact, of course. And one of the short-term effects is that you blow a lot of dust into the atmosphere, and because of the place where the impact happened, you also blow a lot of carbon dioxide into the atmosphere. You blow sulfur dioxide, sulfur trioxide, chlorine, by the way, bromine, which is a major ozone killer. So you have mutation rates going up on short-term effects. So you have a whole series of effects that happen. And impact winter, as an analog to nuclear winter, is one of the effects, and that is the relatively short-term effect. We also have acid rain happening. Among other very short-time effects, you have, of course, the ejection of the hot impact ejector that set things on fire. We have evidence for what has burned, even down to the plant level of what was burning at the time, and it's a very short time effect. So there was a huge environmental disturbance, and you have the different types of disturbances that have different half-lives. And I think the different types of disturbances are also specific to specific animals and plants, that destroy certain habitats, but maybe not others. And some animals that are, for example, there is some buffering going on in the ocean, the top level of the ocean, therefore you have not much extinction among certain types of fish. Those are things that you can reconstruct. The problem, of course, is that because of the compression of the record, and it is very difficult after 66 million years, because you have to go millimeter by millimeter, and the preservation is not always perfect. So it's very
good,
difficult.
Christian. Yeah, no, I'm going to have to ask you all to keep your responses relatively short.
Unfortunately, we don't have that experiment coming up anytime soon.
So the volcanic team, yeah, Evelyn, you.
Well, since Paul mentioned plants, so I feel involved into that one, of course. Mentioning plants, the fact is that if you have this dust in the air, what you have, of course, is a problem with photosynthesis. But the plants are beautiful organisms, and they're very, very flexible, if you want to say so, because they can shed their leaves, and even after some years of time, they can still grow from themselves. And then on the other side, of course, you have the seeds, which can survive hundreds and thousands of years and just regrow again. So you really would need a major disturbance in order to kill groups of plants, for example.
Yep, okay. Thierry.
Okay, this is just first a few comments. First of all, I think that Paul is probably wrong that he put a line at the onset of the Deccan traps saying there is nothing happening. It's a problem that now we have more and more evidences that the maximum of the frequency of the eruption coincide just below, at, and right after the KT boundary. This is really a day of very bad luck, in fact. So I think we have really to think a little bit differently and to ask the question differently. Could we have an extinction only with volcanism? Or could we have an extinction only with impact? And we'll say, no, it's a combination of the two. It's very simple. And moreover, you can see also in the record, in the uppermost maestration, there is a lot of very well diversified groups. We got extinct, like the rudest, almost extinct. Ammonites, you find in LCAF, the GSSP, for the KT boundary. So the last ammonite is found 2 meters below the KT boundary. So that's why we are really to think about a combination of different factors, not just only one.
Good. Okay. So, Paul?
Yeah, no, we're not allowed to compromise here. But I'll just point out that I don't deny that things started happening when the Deccan traps started erupting. What I'm arguing for is that no extinctions happened when the Deccan traps started erupting. And in the best sections we have with the most complete records, then everything goes right at the end of the extinction. The other thing about if the latest dates for the Deccan eruptions show that the peak eruptions are right at the boundary, then it no longer becomes it almost becomes impossible to disentangle the two. So we should just leave it alone and have a look at other boundaries instead. But.
Okay, volcanic team, yeah.
I guess I'll agree with Thierry a little bit.
Shouldn't say non-impact team.
Right, non-impact team. So while it may be important to consider the effect of both, we have plenty of evidence from previous extinction events for which there is little to no evidence for impact. So the precedent is there in the geologic record that these types of volcanic eruptions can cause and did cause mass extinction events. And so why couldn't it be the same at the KPG?
Okay.
I can answer that. Well, I've said
Go
that.
ahead. Because I don't see other questions. Questioners? No? Go ahead, Paul.
Okay, as I was talking about this morning, the only good links are with the ones of the Permian through to the Jurassic. After that, you're hard pushed to find any link between LIPs and extinctions.
So, go ahead.
Yeah, I have a question for Evelyn about the plants. Could it be that all the plants were killed after whatever happened, volcanism, whatever, and then you see that the fossil is undisturbed, the fossil record is undisturbed because the seeds survived? Like all the individuals were killed, but the seeds survived?
Yeah, but when the plants are killed and the seeds survive, then there is no extinction. The extinction means that there's no possibility for the genes to go on. Okay, so
But
if
I maybe misunderstood because I thought you said the amphibians and plants did well after this.
yeah, exactly what I'm saying is that you have certain groups like insects, like plants and so on, who perfectly survive the impact of the Kitty boundary, and which means that they were not extinct. So because since they can survive as seeds, then there is no extinction. They just, like say, they're dormant, if you want, so they're sleeping, and then a few years or 100 years or 1,000 years, they just regrow again. But that exactly means that there is no extinction then, because of that.
Sorry, just to clarify, is that if all the individuals are killed, then you have, the herbivores won't have food. That's why, I mean, it's connected to what Paul said, and then you have the impact of the lack of plants in the rest of the food chain, but you see that the plants did survive after after some time had passed because their seeds survived. But maybe. Should I explain it?
Thank you very much. No, as I said, of course, the plants have this possibility. Okay. In order to be extinct, in order to extinct the group of plants, that would mean that there are no seeds that surviving this extinction. So the litter can go into the food web and be eaten by all the plants and everything, all the animals and everything. That's no problem. But as long as the seeds can still germinate and produce a new plant, that means that that plant was not there for a few hundred years, but it's still there as a seed. And it can still grow again. And that's what we see at the Kitty boundary, that you don't have this loss of diversity in plants and insects, for example.
Okay, I think we have to leave it there. There's another question. Go ahead.
This is for Christian, and if you mentioned this at the beginning and I missed it, I'm sorry. But my question is, what do you know of people looking for a model of the effect of an impact on oceanic crust, which would since be subducted, the impact site? But what would that look like for its signal in the record? Has anyone taken a shot at that?
It's a very good question. Because the oceanic crust is relatively young, the only impact events that we have documented on Earth properly are on continental crust or on the continental shelf. And in fact, because you need a certain size of impact to penetrate down through the ocean into the oceanic crust, and the relatively young age of the oceanic crust, no large impact events have been preserved there, or we haven't discovered it yet. And the problem also is to get the ejecta out from there, because you have, very kind of, if you have several kilometers of ocean water there, a lot of your ejecta will be water, and therefore, how persistent water is in the geological record, so it will be very difficult to detect. If you have large impact events into ocean, they will have environmental consequences, but you will have a very hard time finding any physical evidence of them in the geological record. Now, Nick mentioned that there were large impact events, old ones. We have some in the Archean, and their record is extremely limited. The problem is that the farther back you go into Earth history, the fewer bits of Earth crust are left of that age. So the chance that you detect either the result of the ejecta or parts of the crater itself get very, very low indeed the farther back you go in time. That doesn't mean the effect wasn't there.
I would make one point in response to that, and it seems like a non-starter to say that impacts occurred at the other mass extinctions, but we just haven't found the evidence, because the evidence should be in the stratigraphic record given the expectations of what impactors do and why they cause mass extinctions, which they don't. In that, in a nuclear winter scenario and rain out of particulates is blocking the sun, you should see that rain out of particulates in the stratigraphic record. If it's not there, then it didn't happen.
How sure we are that the Deccan Trap volcanism was explosive enough to put stuff up in the stratosphere? Do we have a handle of that?
I think that is a big uncertainty, and there's various people trying to model this process, and the answer is probably. We shouldn't necessarily make an analogy to eruptions like Toba, which are much more explosive. But in the case of carbon dioxide, it doesn't really matter whether it makes it into the stratosphere or not. In the case of other materials, it may, for example, sulfur dioxide. And whether it needs to be explosive or not is an open question, but perhaps during these long-term fountain eruptions, you simply build up a heat plume, which can then, through buoyancy, transport this material up into the stratosphere and distribute it globally.
Can I just come back? Oh, I just come back in there. The thing about Toba is it didn't do anything. So the Toba eruption 74,000 years ago was an interesting time, but it's very hard to find any effect. There's certainly no extinction there, and it's highly unlikely that any flood basalts were anywhere near as explosive as that, or did as much as that. So it kind of argues against.
So Toba, despite being sort of the largest recent eruption, was minuscule compared to large igneous provinces. And
Not individual flows in large igneous provinces, obviously.
Right, but there are many of them.
Yeah, but it's the size of the flows. I mean, the large igneous provinces have to do the damage by one flow or a very closely spaced series of flows. And
I think the last point is the important part, that yes, you need to understand the rate of eruptions to establish that it can have the environmental effects predicted by the modeling.
Okay, now more questions, or if you want to make a comment, if you agree fervently with something that has been said or disagree strongly, you're also welcome to come to the microphone and make the point. But here's another question.
So I have a logical problem, which is that say the KT is an impact. Why should that mean that all mass extinctions are due to impacts or volcanoes? It could be either or. So I would like to hear your take on mass extinctions without an external cause, like ecosystem collapse or something like that.
I can throw one in addition. There are supernova explosions and gamma ray bursts, and there is some indication that maybe a gamma ray burst was responsible for one of the Devonian extinctions. So I remember somebody, I think it was Doug Irvin, said that it would be really boring if all mass extinctions were caused by the same effect. But on the other hand, we are here because we have been told by Nick to defend one particular position.
So I'm told I'm ignoring people at the back of the hall. So
just one. Yeah. My question concerns the 200,000-year time lag. Biologically speaking, that's a very long time for evolution to happen, adaptation to happen. So what is the chain of events such that the extinction doesn't happen until 200,000 years after the disruption begins?
Well, that depends a little bit about how severe the beginning of the eruption was. You can have a quite slow eruption in the beginning. So then you don't have that much effect on the ecosystems in the beginning, because you don't have that much effect on the climate change, on the atmosphere and so on. But then, as we heard before by Thierry as well, then you have several more pulses. And of course, each of these pulses increases the effects on the atmosphere, and so increases also the possibility of the extinction. And so you would expect to see in the beginning just very
some of species which are more sensible, like today the reefs, like barrier reef is in bleaching, and then you by the time going on, by the pulses going on, you see more and more groups going off the record.
That's a great question. And remember that only 10 years ago, we couldn't establish better than plus or minus a couple million years that these events overlapped at all with mass extinction events. And while we can now say that, yes, they began a couple 100,000 years before and ended a few 100,000 years after, what we really need to know to answer the questions we're asking is actual rates through that period of time, which is what Evelyn's getting at. So that's the next step.
Hello. I have a question concerning the mass extinction rule. So concerning the atmospheric composition, do you think that atmospheric response could be behind the mass extinction alone?
Can you repeat the question quickly?
Yeah. Okay. I think that the extinction couldn't have happened without an atmospheric response. So, can atmospheric chemistry alone play a role in mass extinctions?
I do, yes. For plant extinctions, I think it's almost inevitable. You have to, if something goes wrong with the atmosphere, you can't do it any other way, I don't think, because plants are adapted to such a obviously broad range from the polar down to equatorial latitudes. And so at some mass extinctions, the KT mass extinction is not as severe for plants, but other extinctions, plants struggle. And I think it is a phenomenon of the atmospheric damage that's done. Either you have a global blackout from lots of dust, you damage the ozone layer or something like that. So yeah, the answer lies in the atmosphere.
And could it have been initiated because something other than volcanic activity or meteorites?
Climate change?
Well, the only thing I can think of is if you have a large supernova or a gamma ray burst, as I mentioned before, actually that causes photochemical reactions in the atmosphere. It will destroy the ozone layer and things like this. So are there possible external events that can influence atmospheric composition?
Okay, another question?
So my question's for Paul, and it's really about your hit rate that you were talking about. So 2 comments, and the first is the idea that maybe in some scenarios the system is primed, or the Earth system is primed, for something like a large igneous province to have a mass extinction. I heard an excellent talk this morning where Pangaea was put in, the supercontinent was proposed as that priming. So that was the first comment, so maybe your hit rate is a little bit blunt in that sort of instance. The second comment on that is I wondered whether you would be willing to admit that evidence of links between large igneous province and major climate perturbations or carbon cycle perturbations such as oceanic events was actually something you ought to bring into that hit rate that you presented to the group earlier.
Yes, let's not remember this morning too clearly, but but our debate is about whether they cause extinctions. I agree that LIPs can do interesting things to climate and oceans and so on, but whether they actually cause extinctions beyond 1 or 2 events in the middle of the Phanerozoic is a lot harder to pin down. And you really start struggling when nobody's talking about the Paleozoic, and there's a lot of extinctions in the Paleozoic, and there's no LIPs there, so...
But we could put the same thing that was said earlier about the impactors, that you have subducted crust, and you lose lips through subductions, as well as losing evidence for impact structures, going that far back.
Yep, and then you need proxies like mercury concentrations and things like that. Yes, that's right.
I couldn't agree more.
Okay, so could I ask one? Or are we finished?
Well, the questions have dried up, it seems.
No, I've got one.
You've got one. There's somebody there.
We're just at the back of the room.
hall again. Okay, good.
So we heard this morning that timing is everything, and I couldn't agree more. So to the impactors, how do you reconcile what we assume would be an instantaneous biotic response This is about mass extinctions, not the KPG in isolation. So how do we reconcile impacts with the other mass extinctions that we know occur over either hundreds of thousands, if not millions of years of geological time?
Generally, the more you study a mass extinction, the sharper it gets. So the end Permian's gone from being 10 to 15 million years long to being a few 100,000 years long. And certainly for the Cretaceous Tertiary, or KPG as it's now known, again, that's now got sharper and sharper to the point where most people are happy that things like dinosaurs and marine invertebrates died instantaneously. So it's maybe a factor of how much you study it.
So earlier you mentioned, Paul, that lips, there's very little evidence for them in the earlier Paleozoic extinctions, and that's possibly one reason to look for other things such as impacts, but there is evidence for other things going on during the End-Ordovician, particularly ice ages is the current favourite for that extinction, and also the latest of the Devonian crises is featuring glaciations as well. So why can't you have something like that as opposed to an impact? If you're struggling for a hypothesis, if you can't pin it on a lip, why can't it be something else entirely rather than a meteorite?
You're right, the End-Ordovician is a fascinating event, as is the End-Devonian as well. You need something to trigger that glaciation. It's particularly the End-Ordovician doesn't make much sense as to why, in a relatively warm world, it suddenly tripped into an ice age. So, yeah, have a big meteorite do it. So. Even at the back of the hall, there's no more questions. Thierry, I'll give you a second one.
No, this is just for the End-Devonian and Ordovician. But at least for the End-Ordovician, there is a paper probably in geology very soon from Jones showing that you have a huge mercury anomaly links probably to ellipse. And if you ask to Vincent Cotillo, he would give you the same answer for the End-Devonian. So I don't think that there is some lips for these two mass extinction events, for sure.
Are we allowed? That's evidence that's not published. Are we allowed to talk about that?
Embargo. Okay, well, I think we'll round it up now. Each panelist will now give a round-up statement of about 2 minutes, 3 minutes, and we'll do that in the reverse order. So, Christian, you can start now. Huh?
All right. Well, obviously, I think impact is a very important process, and we're not an isolated planet. There is no invisible shield around the Earth, so we have been subjected to the same amount of impact events as any of the other planets as well. I think it is clear that impact is a very violent geological process that can cause a lot of damage, and especially the large ones, they are capable of altering our environment in very interesting ways. What interests me in this discussion too is that when we look at the evidence for extinction, most of the boundaries were defined well before any cause was determined for them or suggested for them. KT boundary or the Permo-Triassic boundary, they were defined because of paleontological reasons. There was an extinction event going on. And later on, something was found. Now, what we have is evidence that an impact occurred, let's say in the case of the KT boundary, precisely coinciding with that sharp boundary. Whereas on the other hand, there is volcanic eruptions that have kind of a very broad distribution. And I have a difficult time seeing a mechanism how that broad eruption pattern that started before and continued afterwards caused that extinction that was very sharp. I think impact is really the most logical explanation for that. And I was also kind of just finished that thought. Blair, it's only 1 minute, okay? So he gave me 2.5, it's counting. So therefore, Blair said something interesting, said if you don't see it, it's not there. And I was just wondering, we do have very clear evidence for impact. You can link impact with ejecta, with shocked materials, with very abundant platinum group element anomalies. In meteorites, we have 1 million times higher PGEs than in a terrestrial crust. So there's a fairly clear signal. I fail to see that clear signal coming from volcanism coinciding precisely with the extinction event.
Thank you, Christian. Evelyn, now you can give your 3-minute reply.
So, as we heard, there's a lot of meteorites impacts going on through history. So if our theme of today, impact is the main cause of the mass extinction, would be true, that would mean there would have been a lot of mass extinctions, and mass extinction really mean mass extinction, not just simple extinction events growing through time. But as we normally define, there are only really 5 big ones going through Earth's history. So why did the other impacts not affect the mass extinction if the mass extinction were really the main impact? That's on one side. For the other side, as I have shown you, as I tried to show you, at least also with the plants and animals and so on, what you observe, if you look at these extinction events, is an ecological disturbance which sometimes goes over a long time period. As such as a long time period that if former times we said there's, for example, one major mass extinction in the end of the Permian, now we are discussing it over that perhaps there's a multiple disturbance of it going over there. That thing is not possible to come in from one single event like a meteorite impact. Third and last one, as I said, we distinguish 5 major mass extinctions through Earth history at the moment, but we also discuss at the moment the fact that we are living in the 6th mass extinction right now. And you can believe me, if you're not going to the cinema, you don't get the mass extinction meteorite now going on outside.
Thank you, Evelyn. Who's it? Paul, I have trouble counting backwards. Okay.
Okay, I think the best argument in favour of impact causing extinctions is that we have a beautiful example at the end of the Cretaceous. It's the research since 1980, since the original paper, has shown that the extinction timing gets sharper and sharper the more we collect. So at one time, dinosaurs were held as a great example of a group that was fading away fast long before the end Cretaceous impact event, and now most dinosaur experts would agree that they all went rather suddenly at the end of the Cretaceous. And for more abundant groups, particularly marine invertebrates and planktonic groups, again, they disappear as well. This is not to deny that the Deccan traps did interesting things before that, but I suspect if there had been no impact, then the Deccan traps effect would have been rather like the Paleocene-Eocene boundary as a sort of an interesting climatic and oceanic phenomenon, but nothing more than that. And we still have dinosaurs with us today, of course, as well. But, so we wouldn't be here. But, so thank you to the meteorite impact. But if we look back further in time, then okay, there's a good link with LIPS for some events, but the majority of extinctions and some of the more minor extinctions and even some of the large mass extinctions as well, such as the end of the Ordovician, cannot be clearly linked with volcanism, and so then we need to start looking for more sort of tentative clues, of which we have some available, particularly in the Devonian, for other impacts that coincide with extinctions.
Very good, thank you, Paul. And Blair to finish.
I think the point that's worth returning to here is the apparent sharpness of various extinction events. And in my reading of the literature, it is certainly debated about whether any of these extinction events occurred overnight or over tens of thousands of years or hundreds of thousands of years. And the fact that there is no identified impactor in relation to the end Permian and end Triassic mass extinctions, and yet the extinction event is equally rapid to that of the Cretaceous Paleogene mass extinction shows that you do not need an impactor in order to generate a mass extinction that quickly.
Okay, that's it. So I guess we can wrap up now. I'll thank all the speakers, all the panelists, particularly. No, wait. I have to say a little bit more, but, because I have to thank them for doing exactly what they were instructed to do, defending their point of view, having a real debate in which we heard arguments for and against the motion. I think they did very well, and now you can applaud them. And the only thing we need to do is have to have the vote at the end to see whether the arguments of one team or another swayed your collective opinion. So again, who votes for the motion that impacts are not the major cause of mass extinctions? And who votes against the motion that impacts? What do you think, teams? Well, I think it's pretty much the same as when we started. Okay, thanks very much. It was a good debate. Thank you for coming.